Hey, it's me again, and we're doing coding. I also want to ask you all to pretend that I'm wearing a different shirt and that I didn't record these all back to back. Alright, so you're going to find in the slides, or if you're not in the class, in the description of this video, a link to this notebook right here, and you will come up with something like this, which doesn't really look like a notebook, does it? And you just need to open it with Google Colab. If you don't see this link right here, you can drop down, connect with more apps, and just find it. Alright, so after you open it, it will go here, alright, and you'll see the notebook, but you won't actually be able to edit this notebook because I don't want you all changing it at the same time. So you just need to go in, save a copy in Drive, and you'll be brought to a new copy, which you can edit and run and all that good stuff. And we're going to start going through this code and showing you. Now, of course, we did just learn about nonlinearities and convolutions, and of course, we're going to be working with those. This will basically be, though, the same code as our first Pytorch walkthrough, but we're going to show you how to do those new things now. Alright, so of course, like before, we just install the dependencies, we import what we need, we have torch vision, and of course all of these. We also define our hyperparameters like before, so we have our input size, which is set by the task, which is 784, which is 28 by 28 images. We have our hidden layer, which we could set to whatever we want. We have our number of classes, which again is set by the task, and we have our number of epochs, which is how many times we run through the data set. So we'll set this a little bit lower because we're going to do a little bit of testing today. Of course, batch size is something that we haven't gotten to and probably won't be able to get to, at least in the class. On YouTube, we may be able to, which is essentially the amount of data we look at all at once. So the amount of images we're going to look at once, and then we can find a gradient based on all of those images that we generalize instead of just a single image at a time. It's a very useful thing and something that you will like to learn at some point. So our learning rate, of course, we also set. We set something fairly small like before, but we can test around it if we want to try something different. So now we download the data. We're using the Torch Vision data sets, so we can just download them very quickly. These are the generators. It's how we enumerate over our data set so that we can actually do our training. So we load that, and then here's the good stuff. Here's our model. All right, so we're going to start with a very simple model. We're going to start with a just fully connected layers, just back to back to back. And we're going to see how that turns out. So right now we have the fully connected 1 to 2 to 2 to 3. This one goes, of course, from its same size to same size. It's the only way we can have it back to back. I'm actually going to get rid of one of these just to make it a little bit simpler. So we just have 1, 2, 3, which is going to go from input size to hidden size to hidden size, and then hidden size to num classes. So we're going to have that. And of course we have the hidden size being 600, which we set above. So we're just going to define this, run it. That's going to be our first network that we're going to test. Right here, we are initializing our network using this. And then this right here is checking whether we have CUDA available. CUDA is the NVIDIA package. There are these CUDA cores on the new NVIDIA graphics cards that will speed up the training of your network if you have them enabled, this is what this is checking. But in practice in Pytorch, we're going to have to send our network to CUDA vectors instead of the normal Pytorch vectors. It doesn't really matter too much, but it would speed it up, which we're not going to be doing it, but you can do it on your own. Look up CUDA if you have an NVIDIA graphics card. Alright, so now we're going to define our loss function. We're using cross-entropy loss again, which is the loss that I described in lecture, which is essentially treating each of the outputs as a probability. It's slightly more complicated than that, but that's the gist of it, and then we are taking the loss based off of how accurate the top one is. And then we have our optimizer, which is going to be actual SGD. So of course we do already know this one totally, and we are actually going to use it. So there we go. And then this is our training loop right here. It's something very simple. Just going to do 3 epochs of training, and let's see how it goes. So you'll notice that with the just fully connected layers, it does converge fairly quickly. If we look at it, it's converging to reasonable losses in just a couple of epochs, and we'll actually see it drop pretty low. So even with just simple fully connected layers, this is like what they would have in the days before nonlinearities, we still perform pretty well. And actually, if we want to check our accuracy, we get 80%, which is not bad at all. That would be, fairly good for back in the day, like before people knew about, or before people had these multi-layer neural networks and all this. That would have been pretty good, but that was a long time ago. That's not that great today. So now we want to make our first change to the network. So we've talked about nonlinearities. I've hyped them up quite a bit, so let's try actually using one. So here we define Relu. Here's how in Pytorch, this is how we define the Relu layer. So you just use the neural network.relu from Pytorch and all that. You can look up the NN part of Pytorch if you'd like to see all of the different layers that we can include. So now that we've defined this, we don't need to find multiple versions of them if we want to use it multiple times. All Relus are the same, they're just the max function, so we can just do that like so. So we say the output is now going to be self.relu of out. And we're just going to have to put this in between both of the different layers that we have already. So now we have a Relu in between each of the fully connecteds. We don't need it at the end here, we just need it in between them. So now this entire thing is 3 linear layers separated by nonlinearities, so they do not combine, and this entire thing is now a nonlinear function. We need to rerun this to reset what our network is. We need to rerun this to reinitialize as a new network, and we do need to rerun this too because we are passing the parameters of the network into the optimizer. So we need to do that again. And this is all of the parameters, like I've said before, like the weight vectors and all of that, and as we get to convolutions, it will be the kernels and all this too, do all get passed as dot parameters from our network. All right. Then we can start the training, and we can see how well the hype holds up. So you start to see that it seems to be converging slower. So, you know, I've talked up nonlinearities and their importance and all of this, and now we have these nonlinear functions, so we expect this to be wonderful and great and all of that, but it is converging slower, and when we go to check the accuracy, we do see 70%, so it is 10% worse. So what gives? Why is it doing this? I'll give you a moment to try to think about why this is happening on your own, and try to give any sort of compelling reason why this might happen. I'd say think about backpropagation, think about what the derivative of the Relu looks like, and think about why it might be converging slower. And does it actually mean that it's worse? So hopefully you've thought about that for a second. Cool. So I'll give you an answer now. So when we're running Relu, like we saw before, it deletes essentially all of the negative values. So it's getting rid of all of the negative values that are in our network. We aren't passing them forward, and we aren't backpropagating to them. And because of that, we actually have many fewer of our parameters actually updating, especially from an initialization. When we have a Gaussian distribution where some of them are negative, we actually see that we are not updating as quickly as if we didn't have the Relu. Now, that isn't to say that the Relu isn't better. So it's just that we have a very limited amount of data right now. We only have 3 epochs, and we aren't doing any tuning of our parameters or anything like that. So if we were to give it more data, and we give it longer, the Relu would outperform the regular affine fully connected layers. It will actually have a higher bound. So because the affine layers can only be a linear function, they actually cap out earlier. They're only able to get probably around 85% accuracy. But with a Relu, if we were to train it and properly do it, we could get 95 to 98% accuracy just by doing that. So it is a big difference, and I don't want your takeaway to be that Relu sucks. It does converge slowly though, and I want you to acknowledge this fault of Relu and like what that means. All right, so now that we've done Relu, we've done nonlinearities, that's all well and good. Let's get to convolutions. So convolutions are the much bigger step in terms of upping the performance here, and upping like all of these, like seeing this number go down quicker. The convergence will be much faster with convolution. So here's how we define our convolutional layer. So this is an nn.conv2d. So this is a two-dimensional convolution, which is the ones that we've learned about. So we just need to define its parameters now. So we have the input channels. I'll give you a second to think on what that should be. We're taking MNIST. How many channels does MNIST have? That's right, it has 1. So, of course, it's grayscale, so it only has the 1 channel. If it were RGB, it would have the 3 channels. So, keep that in mind. For the output channels, we can pick something totally arbitrary. Let's go with 10. I don't know. So, we're going to use those 10. So, that'll be 10 different 4x4 filters. We set the kernel size here as 4x4. So, we have 4x4 filters. We have 10 of them. We're taking in 1 channel. And then for the stride, we know that our 28 by 28 images are divisible by 4, so we can actually do stride 1 and know that we will actually come out with a proper answer. It's a slight trick for you, but nothing like too fancy. I'm sure you can figure out why that is. So now we end up like with our convolutional layer all set, so we can actually add it to our forward now. So we have our output be self.conv1, only conv, and we take an x. And we need to make sure that we actually change our fully connected layer, so now it takes in the output of the conv1. Now, we aren't actually done now, so we see that we are actually producing a multi-dimensional tensor from our convolution. So we actually have, we have a 10 by something by something. I'm really trying to figure out what those somethings are. You know what, I'm going to change it for you. I'm going to say that this is 7 by 7. How about that? All right, new problem. It's 7 by 7 now. So now we need to decide how big this is. And we know that these fully connected layers, these affine layers, as they might be called, as I've been calling them subtly, we can only take in a vector. So they can only take in a one-dimensional tensor. So we actually are going to need to convert it in some way. So the very first thing we're going to want to do is we're going to want to reshape this output. So we have a three-dimensional output here. We want to make it a one-dimensional output. And how do we do that? Luckily, Pytorch has something built in that is very nice for this. So we're going to use the .view function. And if we use .view and we give it the first parameter as -1, this is going to tell it to flatten our data into a single vector. So we need that because we are passing a one-dimensional vector. So now we just need to pass in the size of it. And if any of you have worked it out on the side with this 7 by 7 kernel size, stride 1, we're going to end up with a 22 by 22 image that is 10 channels deep. So this will be the actual size of the output from this layer. And of course, this is actually not the last thing we need to do. We also need to change it up here. So we need to change its definition so that it is taking in the proper size. So it'll be 22 by 22 by 10. All right, so this is all set. This network is valid now. It should be able to be run. We just need to run through each of these. But here we do actually have one more thing we need to change. I'll give you a second to see if you can figure out what it is. So it is this right here. So you actually know what this does now. We are changing the view of the images, which is the input that we're getting, and we are making it a single dimension vector. We were doing this before because we only had fully connected layers, and they, of course, need a single input. But now that we have a convolution, we actually want to have a multi-dimensional input, so we can get rid of that now. All right, so now this is all set, so we can start to train it, and let's see how it behaves. So off the bat, nothing too spectacular. It's staying roughly around 2, which is what the Relu did. But now we see that it is dipping down quite quickly, and it is going much lower than either of the other two did before. So even with this simple one convolutional layer, we got our loss all the way down to 0.3, like into the under 1 very quickly. And this is only with a little bit of data, mind you. So let's try actually checking the accuracy. Again, we need to make this same change here. And now we can run it, and we should get pretty high. That's 86%. That's pretty decent for just 3 epochs and without doing any tuning whatsoever. We didn't check for different hyperparameters. We just wung it. So now let's try something new. We're going to try 2 convolutional layers. So like I said before, we can have as many convolutional layers as we want. So let's try adding a new one. So if this one's going to be convolutional layer 2, we're going to have it go after convolutional layer 1. So of course, its input channels will actually be 10 because the output channels of the one before it were 10. And it's a general paradigm. It comes from AlexNet if you want to go look up that paper. But what we tend to do is we have the kernels across multiple convolutions get smaller, but the number of filters get bigger. This has sort of just been proven to work empirically. If you want to try to convince yourself of why that's a good idea, go for it. But let's try upping the number. So let's say 55. Kind of a random number, but let's go for it. And let's have the kernel size be 2. 2 by 2. All right, 2 by 2. And we have stride 1 still, let's say. Okay. So that seems all well and good. Okay. Now we do have a different size, though. So I'll let you try to figure out what it is on your own. And then I'm going to type it in a second. So now we have a new size coming out of here. So we're going to remove that. Then we're going to have our output is now going to be self.conv2, taking the output. So we're going to do 2 convolutions on it now. And we're going to need to change the input size with the view. So hopefully you've got it by now with all that typing. It's going to be a 21 by 21 by 55. So there are 5 channels, and then we get 21 by 21. We have from this 7, we got 22 by 22. And then if we do, you can just use the equation if you'd like, we get 21 by 21 out of this. All right, so we need to make this same change up here. So we're going to take the same value. This needs to be that. All right. So now this should all work out. Let's see if it does. And let's see. So we run through these, and let's see how the training looks. All right. So again, this is just with 3 epochs, very small amount of data. We see that it starts converging. It seems to be converging very quickly, and in fact it is. And we'll see that it will train very well, actually. So let's see that. It goes all the way down again to 0.3, but it tends to stay down there. We have many more parameters. We've actually added a lot of parameters, which, you know, there is a trade-off between adding more parameters. There's more things we're updating, but you see it doesn't slow it down that much, and we are getting much better performance. And let's see how the accuracy actually turns out. So we got 89%, which is pretty swell. So let's try doing this except with more data. So instead of just 3 epochs, let's do 10. I'm going to need to vamp a little bit more, but I believe in myself. All right, so now with 10 epochs, let's see how this turns out. Now again, this is without us, you know, messing around with the hyperparameters at all. Did I change something wrong? Why is it going up? All right, that's a bit odd. Interesting. Did I change the wrong thing? I might have changed the wrong thing. No epochs, no 10. Strange. Is it going to go back down? Huh. Well, this is interesting. So I'm guessing I'm putting you a little bit behind the curtain of training models and what it feels like, because there's a lot of debugging that goes into it. This is not a mistake. This is on purpose. You see, actually, it did go down pretty low there. So I'm kind of curious how this is going to turn out. You can put your guesses in the comments or whatever as to how this is going to go. It could be that we are doing so that actually went down very low. Huh. Let's see how it turns out. Yeah, I'm curious myself. This is sort of the nature of playing with machine learning, is sort of just figuring stuff out. Let's see how it turned out. 95%, so pretty damn good. So yeah, these losses are a little bit not indicative of how well it's actually doing. We're going to talk about this actually more in the next lecture. That's a pretty good segue about why these losses can be deceptive and why we actually don't necessarily want to reduce these as much as possible. So this actually turned out pretty well. This is pretty good accuracy. I am going to wager that you guys could actually do better. So I'm going to say download this, see, play around with the sizes of these filters, see if you can figure out some filters that work, and see how good you can get the accuracy. I would expect that you should be able to get 98% if you mess around with it, but if you can't, that's totally fine. Just try to figure out how it works. All right. Hope you enjoyed, and I'll see you in the next one to talk about all this nonsense. All right. Thanks for coming.